Welcome everybody to this webinar. Thanks for dialing in and listening. So this is about the world's largest ISTD project, and normally we don't brag about things when they're big, more about them when they're small and efficient and cost effective. But I hope to convince you that this actually was a really cost effective in situ thermal project. And due to the scale of the contamination, we had to have a large system out there to handle the challenges. Please know that at the end of this webinar you can ask questions by typing them in. You should have a little control panel where you have questions we showed here on the left. You can also, towards the end, you can raise your hand, and there's a place you can do that, and then I can see it and I can unmute you if you prefer to ask your question verbally. So all of that will happen at the end, and this is scheduled for about 30 minutes or so. I hope to keep it close to that. So type in questions anytime or hold them to the end and raise your hand for that. So a little preview here. This talk is not just, to tell you, yeah, we cooked another site and it was great. It is to inform you about some of the challenges you can face when you have a large site, how certain things that make a little difference for a small project can make a big difference for a large one, and how we address that as a team along with the consultant O'Brien and Gear at this site and the client as well. Shallow groundwater is one of the things you'll hear about. It can present some really good challenges that we had to deal with. One thing we thought was really successful in this project was that we talked a lot before we started and before we finalized the plan for this about what could happen. And then we, along with the client, made some good decisions, we think, about proactively preventing some things from happening that could have cost a lot of money if we hadn't done it. And also, when you have this large of a project, you've got to really pay attention to optimization of everything and minimize the utility usages and the environmental footprint and the cost, of course, as you are implementing. Small changes and improvements can make a big difference for the project in the long run. All of this hard work was really not done by me, but some of the real people working on the people really working at the project. Ken Parker was our project manager, and you see Gary Engel and Jeff Levesque from O'Brien and Gear, and Ralph Villica from Villica Consult, and they were very instrumental in the way this project was successful. They're co-authors on this paper, which we are happy just got approved about a month ago for publication. And I'll repeat the reference that you see here at the bottom in groundwater monitoring and remediation. That will also show at the final slide, so you'll have time to write it down then if you want to look this paper up. So the Teterboro landing site had a lot of manufacturing and other things, and for the redevelopment that was planned, that there was a 3.2 acre hotspot, and you can see it there in yellow inside the red square. The red square was the former building that was at the site, and a lot of chemicals were spilled underneath that building. It's right next to the Teterboro Airport, and you can actually see the Manhattan skyline from this site. And if you look to the down on this drawing, you can actually see the Freedom Tower and all that. So the 3.2 acre hot spot or source zone was divided into four zones actually, and you can see here different depths in the different little shapes. The deepest point was about 12 meters or 40 feet deep, and that's how deep the contamination was. That exceeded 10 milligrams per kilogram. In other areas of the site, it wasn't quite as deep, so we treated to a shallower depth. All of that, of course, to minimize the total volume and the utility demands of the thermal treatment. The other reason for having four zones is that when the site is this large and towards the end you're collecting soil samples to confirm that you're done, you can't you can't take soil samples over a 3-acre site in less than 3 or 4 days, and then you have the turnaround. So you really want to narrow it by having some zones, and then take all the samples in one zone, and declare victory and stop heating that, and then you move, continue heating the other ones until you're done. And putting it in zones where each one had its own statistical analysis associated was a way to make that much more easy for us towards the end. So the contour of this was the 10 milligram per kilogram line for the contaminants of concern. You see them listed up there. We were expecting 30 to 50,000 pounds of mass to come out, and that was roughly what came out. The treatment goal was 1 milligram per kilogram for each of the chemicals inside this zone, from top to bottom. So a pretty good objective there. This would allow for redevelopment of the site when these goals were met. The client and O'Brien and Gear chose in situ thermal desorption as the best, most effective thermal method for this, and we decided to go to what is T2 on the graph to the lower right. So basically, we are heating the site to the boiling point of water. The heaters themselves get a little hotter than that, or quite a bit hotter than that, but in the 90 or more % of the volume gets to the boiling point, and that's enough to get the TCE and PC and the other contaminants to vaporize and come out. In the field, it looks approximately like this. I've taken a simplified picture here with heaters with 15-foot spacing. You see a simple ISTD heater with a little box at the top. A cable goes in, a cable comes out. The green cables are grounding wires, and you see an insulated vapor cover. It's air-entrained concrete, and that's as simple as this process is. We also have some multi-phase extraction wells, and they all are attached to the vacuum manifolds, and in the fiberglass pipe you can see there hanging is such a one. It's a vacuum manifold. We also have a liquid manifold when we're pumping water at these sites. Down and inside each heater casing is a very simple resistive rod that is our heater element, and electricity runs inside of it, inside of the casing through this stainless steel rod, and it's protected from shorting out by these ceramic beads you see along the length of the hairpin heater, and it is operated by thermostat controls, just like you have in an oven. As an example of this, silicon control rectifiers like the one you see here can be used to that. So they simply sit and control the electricity to the heater circuits, and turn them on when you want more heat and turn them off when you're hot enough in the well, and it operates automatically. We can also program it to pull more power into the ground at off-peak times and less during high demand periods to even out the load for the grid when we have a big project. This site had very unique challenges, and on this slide you see an original the black punctuated line right underneath the blue fill layer is the original land surface, and as you can see, the blue line is the water table. At times it was actually above the ground, and one of the things that was really challenging here was the fact that the groundwater actually started rising in the middle of this project, and by the time we had placed the fill layer you see on top, the water level was up there, and I'll talk about that a little bit more. You see the heaters go from top to bottom, and we have multi-phase extraction wells that also are screened across the treatment zone, and horizontal vapor collectors which we placed in the fill layer. We had to create that vado zone to have a place for all the steam and vapors generated to come up and get captured. So the site had about 900 heater borings to cover the 3.2 acres. We put in 35 multi-phase extraction wells, and as you'll see in a moment, we were happy we did that. And then we had 116 horizontal SVE wells placed in the fill layer, and 80 vertical strings for temperature monitoring with thermocouples from top to bottom. One of the things that was really expensive was the drilling and the installation of more than 900 heaters and all the other infrastructure. So one of the inventions here was to actually adapt a head from a pile driver. You see it on the left, putting sheet pile in at a site. On the right, you see an adaptation of that to our heater casing, and we were able to direct push a lot of the casings in. Somewhere around 700 of them went in very smoothly without obstructions out of 900. And what that did was it reduced the drilling cost tremendously, and also there's no cuttings when you do it that way. So just an indication for other sites, if you can do MIP investigations or scabs or other direct push with a 2-inch probe, you can, with a little more power, probably also install our heater casings with similar direct push methods, which in this case saved roughly $500,000 compared to drilling, and then you don't have the off-site disposal of the cuttings either. So the site used to have a huge building, and what you see here in the little gray squares are footers from the original building. So when we were about to start the drilling phase, we went out there and surveyed in all those locations for the heaters, and we had to try to avoid hitting these old foundations with a direct push method. And so some holes were dug to verify where those were, so we knew that the survey had the right grid, and some of them were actually excavated. And here's an example of one, and you can imagine that it's nice to not hit those when you're drilling and installing your heaters or your wells. A lot of them were left in place and simply heated and treated along with the dirt around them. So they didn't present a remediation challenge, but of course they presented a challenge for installation of the heaters and the wells. If you hit one, your direct push was not going to work, and you see a couple of pictures here of a can that was bent and cracked, the tip of a heater can that hit something really hard. So a lot of places we actually had to say there's something down there that's too hard for a direct push, and then we used a more traditional rig just in those locations to get our heater casings to depth. So we placed a 4-foot thick fill layer, and we had horizontal vapor collection wells in that layer. Here's a picture from installation of them. And as you can see, the groundwater table, which was supposed to be a couple of feet below grade, actually was above original grade at this time. It had been a very wet winter, and we had shallow groundwater to contend with. So in this case, we used the 35 multi-phase extraction wells we had also installed, and we had an additional 30 days or so of liquid extraction before we started heating. And that's because when you start heating and you generate steam, you need to have pneumatic control, so you need to have your vacuum extraction screens exposed. So you couldn't have them drowned like you see in this picture, so that's why we had an additional month of extraction before thermal treatment began. During thermal treatment, we also had some events of the water being relatively shallow. So what you see here on the left is a pipe from the horizontal vapor collectors exiting the ground, and we had water sitting in some of them. So what we did was we drilled a hole and put a tube down to the bottom and into the horizontal vapor collector, and then we're able to simply pump it out with a dual diaphragm pump. We're able to pump water, and we put it straight into the vacuum manifold line, so it would run to our knockout pot and be collected there. So Steve here on the left is holding the extraction screen there, not screen, the valve, because it wasn't flowing, it was cold. But after you evacuate them by pumping the water out, they would start to flow steam, and they would work again for pneumatic control and for vapor extraction. So one thing on a large project, and actually also on any thermal project you have to be aware of, is whether the groundwater will flow across your zone and whether it will make it hard to heat and reach your target temperatures, and also whether you potentially could have some of it escaping from your treatment zone. So we model that, and these are some sketches just from a setup of a model. Down now you can see just a schematic. If you have the water stands still here on the left, you can get to your treatment temperatures fine. We can model, say, a 5 gallon per minute flow across the treatment zone at a certain location. The middle figure shows how, when it comes in from the left, you'll have some cooling happening upstream, and you won't be able to get to your treatment temperatures where the water is coming in. You might lose a little bit of water on the down gradient side unless you're pumping. And on the right, you see more of a problematic zone. We modeled 10 gallons per minute escaping there, and you see at that point, if we're not pumping enough, you would have warm water, potentially rich in your solvents, leaving. So it's really important to know about these things up front and build into the design methods of hydraulic containment. So we did an analysis for this particular site where we varied the groundwater inflow. You see it on the x-axis here, and then we estimated, based on our numerical model, both the energy usage and the duration it would take to get to treatment goals. The red is the energy usage, and it refers to the right y-axis here. You can see that we had, if the water stood still, we were around 26.5 million kilowatt hours estimated, and if we allowed as much as 4 meter cubes per hour to run across the site, we would be up around 37. So a million kilowatt or 10 million kilowatt hours difference, which has a cost impact in the range of $1 million. So it was pretty important. Same way, it has an impact on the duration and the rental of equipment and the labor, and that's what you see on the blue line there. The actual performance are the dots in red. You see that we were able to use a little bit less electricity than the 26.5 million estimated. But instead, we also had to run a little bit longer, or quite a bit longer. You see the blue dot up there. We had an area in the middle of the site that just we had to sample it 3 or 4 times before the goals were met, and we had to put in 4 additional heaters to get that little area up to speed and to be treated. But generally, this kind of analysis was used to say, okay, if we can stop the groundwater, we have a major improvement. And the client decided, based on that yes, we want to prevent the groundwater from moving during thermal treatment. So the decision was to put a sheet pile wall around the whole thing, and you see it in pink around the edges, and you see a picture from when it was installed. And it was the same machine that put in the heater casings, so they made it a little easier that we were both pushing a sheet pile wall that was tied into the clay below, and the heaters in with the same rig. Another challenge for a large site when you want to do something like this and get done within an 8 or 9 month operational period is, if you do it in one shot, you need a lot of electricity, in this case 11 megawatts. And it was decided to not have one big power supply, but to actually have 3 of them. And you see one in the foreground here, you see one to the left in the background, and there was a 3rd one as well. So transformers that can give you 3 or 4 megawatts instead of one big one giving you 11 was a more cost-effective solution. Cable runs are shorter, you don't use nearly as much copper, and also those are simpler and easier to procure and get out to your site. One of them, of course, was also fueling the effluent treatment system. In this case, we had 30,000 pounds of chemicals, roughly, and chlorinated solvent and fluorinated freons, CFC 113. We had a system of about 3,000 SCFM capacity on the vapor side and 50 gallons per minute on the water side. Remember, we had 35 MPE wells, and for the dewatering phase and for keeping the water level modest, we needed a decent size groundwater treatment system as well. So in broad terms, this big equipment operated really well during the whole period. We had a little complaint about noise from one neighbor, but those were dealt with. So on a big site like this, it really matters when you are finished with your treatment. So what did we look at? We looked at temperatures in the ground, we looked at the mass removal trend, and then we looked at the final soil concentrations, which was the real strong metric that everybody were interested in so that redevelopment could move forward. Temperatures, I show just example average temperature profiles from the 4 decision units I showed you before. And as you can see, temperatures kind of climbed up nicely from top to bottom and reached the boiling point of water and slightly above 100 degrees because there's a little pressure as you move below the water table. But in general, we were really happy with the heating, and we got nice proof that we had heated the whole 3-acre site down to about as much as 40 feet to the target temperature, which was boiling. And then we kept it there for a while and took the confirmatory soil samples you'll see in a moment. Before doing that, we needed to just verify that we heated everything. Also, the fill layer that we placed on top, and one of the indications of that is the temperature of the vertical legs on the horizontal vapor collectors, and we plotted it like this. A red color means hot, it means flowing horizontal vapor collector. If it's not so red, it was cooler, and those are the ones we were troubleshooting and then going out and pumping water out of to get them to flow. And so that's another thing. You do not want a cold layer on top of your treatment zone. You want to keep that hot, and you want to get all that steam to flow out so your chemicals do not accumulate and condense in a cool top layer. One of the methods we use at other sites is infrared photography. Here's just an example where you can look from a man lift. You see where it's nice and hot, and that reflects in that there's heat loss through the vapor cover, and that's where it's red. Other areas that are not yet up to temperature will show in blue, for instance. You can use the same infrared technology to quickly, without touching anything, check your manifold pipes for where the hot stuff is coming from. Here is an example on the left. The vapor manifold is cold. It's flowing towards the right. And then we have a hot extraction well providing steam to the joint stream. And as you can see, it goes into the manifold and turns right, and the manifold is warm on the right side. That's an easy way to go out there and see where you need to optimize without touching everything. Mass removal was the second metric I told you about. Here in blue is basically the daily removal in kilograms per day, and some of you will, it's on the right side, it's as much as 760 kilogram in one day. That's 1,500 pounds of chemical in one day. You'll have seen other source removal projects, even thermal projects, that have over the whole life of the project extracted less than that. And this in one day was about 1,500 pounds in the peak day. So overall, we got about 30,000 pounds or 13,500 kilograms. And as you can see towards the end, very little was coming out. And we just had that one little zone that was recalcitrant, and around day 210 we got the extra heaters put in that area, and you can maybe see a little blip down there in the blue curve. A little more mass came out, and then the goals were met, and we were able to turn off the system. Of course, we had to prove it, so there were almost 300 soil samples collected, and they were collected in all kinds of depths and over all the zones. You can do it with a compact rig that goes in between the heaters. You get compact core or intact cores out. They're lined and they get cooled off. And we have EPA approved methods for doing that, and then for extracting and sampling the material under cool conditions. And when we do that, we get really reliable soil concentration data. For this site, you see on a logarithmic scale all the different chemicals of concern down below, and you see the blue bars show the highest concentrations before, and as much as 10,000 milligram per kilogram of CFC-113 was found with a goal of 1. So we needed 4 orders of magnitude reduction on the worst chemicals to get below our goals. The goal was 1, you see the red line, and the actually achieved post-thermal concentrations, maximum concentrations, are the brownish bars you can see there. So all goals met. All the 296 samples were used to confirm this. So in summary, it was a big site. It was 3 acres. It was 123,000 cubic yards roughly. And it was not an inexpensive project, but when you convert it to unit cost, it was about $120 per cubic yard treated for the thermal component of this remedy. The energy usage was about 249 kilowatt hour per meter cubed, or 174 kilowatt hours per cubic yard. That's another metric that scales reasonably well with size, but it's a kind of a new metric for waterlogged sites like this one that were saturated from top to bottom, and it was pretty astonishing that we could get the power usage as low as this. So good result for that, and the energy bill was lower than expected. And as I said before, roughly 30,000 pounds removed, and for the thermal part it was about $500 per pound, which can sound like a lot, but the driver at the site was so strong that the redevelopment was much more valuable than the cost of the remedy, and the only other reasonable alternative was excavation, and we don't know exactly what that would have cost, but it would have been extremely difficult and also extremely costly with the shallow water table and the sheer size here. So with that, I thank you for listening, and please remember you can type in your questions, or you can raise your hand, and I will try to unmute you if you do so. And it's